Welcome to Unit 3, Video 3.1, Types of Energy and Conservation of Energy from Chapter 6 in your book. If we first start thinking about energies, we have to look at all the different types of energies that we have so that we can determine what it is we are looking for and what it is we're really talking about here. So let's start with kinetic energy. We know that kinetic energy is the energy of motion. So anything that's moving has kinetic energy. With potential energy, we have to break it up into two larger or smaller categories. First is gravitational potential energy, which is due to the position of an object in a gravitational field. So again, due to the position of the object in a G field, in a gravitational field. Now, elastic potential energy is due to the stretch or compression of an elastic material. Sometimes the stretch is called an elongation. So due to the stretch or compression of an elastic material. Now, the one thing that you have to remember is while the kinetic energy is the energy of motion, potential energy is really a stored energy. So when we are talking about potential energy, it's something that the object has because of its state. We also have a few other types of energy listed here. We have thermal energy, which is due to the temperature of the object. We have chemical energy, dealing with the bonds that the particles have within it. Nuclear energy, having to do with the motion of the nucleus and the interactions of the particles in the nucleus. Electromagnetic, which is what we're completely dependent on with our electricity in all of our fancy gadgets. And of course, we have mass, which is what Einstein told us that we could get energy out of mass if we get the mass moving fast enough. We're going to stick this chapter and this unit to just looking at these two over here. The combination of kinetic energy and potential energy, no matter the kind, is called mechanical energy. And that's really what we're going to focus on in this video, and mostly in this chapter as well, is about mechanical energy. So we're going to be looking at the interaction between kinetic and potential energy, either kind of potential energy. So let's look a little bit more in detail about kinetic energy, the energy of motion. The formula for kinetic energy is Ke equals 1/2 mv squared. The Ke sometimes is also written as an E sub k. It doesn't matter which way you write it. I go back and forth sometimes as well. The m, of course, is mass, and the v is the speed squared. Any object that has motion will have a certain amount of kinetic energy in it. So the change in velocity or speed is what's going to change your kinetic energy. The potential energy, or our stored energy, if we look at gravitational potential energy, we have P E sub g. Notice that you have to have the g there to clarify that it's gravitational and not elastic, which is the EL. Gravitational potential energy, because of the gravitational potential energy being due to the position of the object in the gravitational field, we have to talk about the object's weight. So mg being the weight, and then times h, or y in this case, because it's a vertical height. And y is the vertical height above a 0 point. So it's the vertical height above 0. Now, we're going to talk more in detail next slide about where you decide your 0 point is, but for the moment you can just think of it as the ground. When we talk about elastic potential energy follows a rule and the equation of 1/2 kx squared. K is the spring constant. The spring constant varies from spring to spring. It is basically a measurement of the strength of the spring. So the stronger the spring, the higher the spring constant. The x is the elongation. Or compression. So in other words, the x is how much the spring has been changed from its original length. This comes from another law, which isn't really a law, but it's a rule that we call a law, Hooke's law, where we say that the force applied on an elastic material is equal to the spring constant times its displacement. This is typically how we find the spring constant. Knowing how much force we put on a spring and its elongation, we can determine the spring constant. If we look back at just the energies up here now, and we think about how we measure energy, energy is measured in the units of joules, which is abbreviated with a capital J. In order for you to have joules as units, your mass must be measured in kilograms. Oops, sorry about that. That K doesn't look anything like a K. The speed must be measured in meters per second, and the vertical height along with the elongation or the compression must be measured in meters. If you have different units than this in your individual mass, velocity, or distances, then you are not going to end up with joules for your units of mechanical energy. So keep that in mind when you're solving problems. Okay, so let's take a look at the what happens with elastic potential energy first. Okay, so we have a set of springs, and let's say we hang 100-gram mass on one. You can see that it extends at some point. Now, if we look at Hooke's law, we can see that if we put 250 grams on it, it extends longer because it has more of a force on it, so the extension or elongation is greater. If we want to talk in particular about the energy here, I'll keep this one at 100 grams and it's steady and we're not going to move it, but let's change the spring constant of this third spring. It has the same mass on it, so if the spring constant is the same like they are now, they'll have the same length. But if I make the spring have a harder quality to it, or have a larger spring constant, notice it doesn't extend as long. Whereas if I go the other way and make it softer, it extends quite a bit higher, or quite a bit longer. So the spring constant is what's determining the stretch of the spring.